In complex networks, engineers track average anomaly across active, visible nodes. If red nodes simply break off and disappear, the dashboard gets quiet. This monitoring strategy creates a false recovery signal. A shrinking error metric can easily mask a network that is actively collapsing. The metric in question is active frame anomaly, an average computed exclusively over the nodes that are currently participating in the network. If a system dashboard reports a declining anomaly signal, the underlying reality is ambiguous. The network might be healing, or it might simply be dying. To test the limits of this metric, researchers built a rigorously controlled, mass-conserving graph dynamical simulation. Local anomalies spread through adjacent nodes, while interventions like local repair and dissolution dictate the network structure. This chart captures the simulation's most puzzling output. The two far left bars show distinct network states with identical active anomaly signals. Yet their functional capacities, the center bars, are violently different. One operates perfectly, the other is dead, confirmed by the rightmost failure original disparity. This is a matched twin. It occurs when two conflicting network realities produce the exact same active monitoring signal, yet possess completely opposing viability. The simulation recorded hundreds of these matched twins. Their existence mathematically proves that active frame anomaly reduction is strictly insufficient to infer functional recovery. The first mechanism driving the statistical illusion is dissolution. In a heavily stressed system, highly anomalous nodes are often removed, disconnected, or naturally drop off the network. Look at the arithmetic of the active frame equation. As damaged nodes are removed, the total active population shrinks. This denominator collapse forcefully drives the average anomaly value down. This chart displays metric means across 1,648 false recovery frames in the random geometric graph testbed. The active anomaly registers as incredibly low, while the original frame failure metric proves the system is nearly obliterated. This is classical survivorship bias, operationalized into network dynamics. The system looks healthy entirely because the dead components are no longer being counted. Any network measurement protocol that ignores missing or disconnected components will mathematically misinterpret fragmentation as restoration. The second mechanism pulling these metrics apart is network geometry. Identical anomaly burdens produce wildly different consequences depending on where the damage sets relative to the work being done. This diagram shows 5 routing layouts. The base graph houses the anomaly seed. We measure viability through effective conductance, evaluating data flow between source and sink pairs. Compare near seed with far from seed. One forces routes through damage. The other steers clear. If the demand paths bypass the damaged region entirely, the system functionally survives. The ambient volume of error mass elsewhere in the graph becomes irrelevant to the user. System viability is never a global property. It is strictly defined relative to the specific geometry of user demand. We also have to account for beta, the anomaly capacity coupling. Beta dictates how aggressively a local error suppresses the conductance of a specific path. At low beta values, anomaly weakly suppresses capacity. This creates a massive decoupling between what the dashboard shows and how the network actually performs. This heat map plots functional decoupling across beta values and routing placements. The left's broad green area shows where the anomaly signal loses predictive power. Compare the right's extreme data points at maximum coupling. Near seed paths show tight correlation, but far from seed routes maintain heavy decoupling. An anomaly signal cannot predict system failure unless it explicitly blocks the required demand path. There is a built-in bias to the random geometric graph model used so far. In geometric models, physical distance usually guarantees graph-theoretic distance. To stress test this, researchers used a Watt-Strogatz topology. This introduces random topological shortcuts, breaking the rigid correlation between physical space and routing distance. This chart tracks the protective effect of distance as the shortcut probability increases. As the p-value reaches 0.25, the top lines drop sharply. The protective isolation of the far from seed placement attenuates. Because shortcuts bypass physical space, spatial separation collapses. Demand paths that seemed safely isolated are suddenly exposed to the damage zone. Demand relative function is governed entirely by graph-theoretic separation. Geographic separation is an illusion if the network topology allows shortcuts. Armed with survivorship bias, demand path routing, and topological distance, the matched twins paradox becomes clear. The failed twin lost its active mass to dissolution. It severed its critical source sink routes, while dropping the failed nodes off its accounting frame. The average anomaly looked low because the dead nodes were deleted. The healthy twin achieved the exact same anomaly reading, but it maintained original frame structural integrity and preserved its demand relative routes. Single-frame scalar metrics compress radically different failure modes into a single deceptive number. Anomaly reduction alone must be discarded as a singular proof of recovery. A rigorous assessment requires 3 checks: map original frame failure accounting and absolute structural integrity, then explicitly measure effective conductance across the precise paths that matter. The absence of a visible threat doesn't guarantee a system is capable of performing its task. Tune recovery is verified by retained structure and functional capacity, never by the quietness of remnants.